we'll be discussing isoquants. By definition, whenever we're dealing with isoquants, we're dealing with production. Companies undergo production, and in firms, institutions would want to maximize production. At the same time, they would want to minimize their costs. So with two functions, one being the production function and one being the cost function, when these two meet, we call that constrained optimization. Constrained optimization is mainly about maximizing one whilst minimizing the other. So when we're dealing with isoquants, we're dealing with lines that join to the lines that join points that offer the same levels of output when combined optimally. So an isoquant is derived from the quantity Greek word which means equal. So when we're dealing with isoquants, we're using a geometric representation of the production function, where we're going to draw lines that join points that offer the same production. So production has two key inputs. We have labor and capital. So a function has two key inputs, labor and capital. These will produce our output, which is denoted by the letter Q. So the L stands for the labor, whose reward is what? A wage. And the K stands for the capital, whose reward is a rent. So these two are all combined together, they will produce an output. So the reward for hiring capital units is the rental. So by definition, production is a conversion of raw materials into finished products or output. So isoquants are simply curves that will offer the same points of output. For instance, here we have what? Labor, and here we have capital. So you may have 12, 12, 12, 12. Maybe you may have 13, 13, 13. Maybe you have 7, 7, 7, 7. Other numbers 4, they're just jumbled. 5, 7, 3, 2, 4, 1. So they'll ask you to identify the isoquants that are here. So you discover that they're in a secular mode. This is our 13. This is our 12. This is our 7. So these points show the optimal combinations of labor units and capital units to forming these convex curves. These curves which are giving the origin the back. These curves are called isoquants. So the characteristics are that the isoquant on top offers the highest production So we have isoquant 3, isoquant 2, isoquant 1. Now these points of production could go even as much as 7 when we are unconstrained. But because everything in this world is bound by scarcity, we are bound by what we call a budget line. Budget line is simply a constraint of a budget. You know, production is characterized by costs. So the production costs in a firm are given by the wages for labor and rent for capital. So the point at which the budget line kisses the isoquant is a point where you as a firm are optimizing with your production. So at point A, you're producing how many? This is 7, this is 12, this is 13. So at A, you're producing 12 units with a combination of 4 laborers and 3 units of capital. At point B, you can produce 7 units of labor with 3 units, 7 units of output with 3 units of labor and maybe 2 units of capital. And at point C, you'll be producing 13 units of production with 5 laborers and 4 units of capital. Now the figures I'm putting are just arbitrary. I'm trying to prove a point. That at point A, you're optimally using your resources because you are working within the budget. At point B, you're being inefficient. You're being wasteful. At point C, it's unattainable because that is working outside your budget. So constrained optimization is basically about combining your production function with or subject to your constraint. You're simply trying to produce more within the little resources that you have. And so we call this constrained optimization. Constrained optimization. So the Lagrangian function is one which we use to optimize production, where the F function, which is in terms of labor and capital, is subjected to the lambda, whose constraint is under the function of the cost, where rent for capital and wages for labor are subtracted from the cost function. So this is what we call constrained optimization. So at point
kindly repeat the meaning of L.
All right. What I said,
You said land.
The L here is Lagrangian. So this is a Lagrangian function which is used to combine 2 functions in one. So this Lagrangian function has 2 components: the production function and the budget line. This is the lambda, the multiplier. So the optimal production of a firm will occur at point A, where you have the optimal bundle. At this point, the marginal product of labor if you were to divide it with the labor reward, which is the wages, you equate this to the marginal product of capital, which you divide by the rent. So this is a summary of the Lagrangian function. We call this the optimal bundle. So every firm, if you're a manager, in this case, this is one course that entitles each one of you to be called what? Managers. A manager, you want to ensure that production occurs optimally, no wastage. So you would rather produce at point A. You'd rather produce at point A. So the characteristics of isoquants are as follows. Number one, an isoquant slopes downwards to the right. Number two, an isoquant is convex to the origin. Number three, an isoquant is smooth and continuous. Number four, two isoquants do not what? Intersect, or they do not crisscross. These are the characteristics of what? Isoquants. They are parallel to each other. Are we together on this slide? So they are actually contour lines which...
Sorry, I have a question.
Yes, please.
Yes, they said two isoquants do not intersect. What was the reason?
So the two isoquants, what they mean that they do not intersect, they're parallel. They can never be like this, because we have already said that they're convex. So production at each and every point here, if this isoquant is giving us what? 7. This isoquant is giving us 7, this one is giving 10. It obliterates the rule at point A where they're meeting, because you cannot have a point where you're giving two contrasting outputs. So they are convex because they give each of these points that lie within this same curve have the same what? Production.
All right. Okay. Thank you. It makes sense.
All right. So they are contour lines. They offer the same quantity of output while changing the quantities of two or more inputs as shown below. So this point where the budget line kisses the indifference, or the isoquant kisses the budget line, what point do we call this? What point do we call this? Point where? Pardon?
Marginal rate of substitution.
Good.
Marginal rate of technical substitution.
Marginal rate of technical substitution is simply the point where the budget line and the indifference curve are tangent. All right? Point at which these two are tangent. So this is where optimal production occurs. So the marginal rate of technical substitution between two factors of production, which are labor and capital. That point is a point where production is proportional. It's a point where production is efficient. point where production is optimal. So this point occurs when the marginal product of labor divided by the marginal product of labor divided by its what? Its wage should be equal to the marginal product of capital divided by the rent. So we'll see how the computations are done. So isoquants and indifference curves are used interchangeably. They have a similar principle. Of course, the indifference curves show or illustrate points that offer the same utility and the points that maximize your satisfaction, which is utility. Isoquant, on the other hand, deals with minimizing costs at the same time maximizing production. So isoquants and isocosts are all parallel to each other. They are drawn along what are called isocosts. So the isoquant and isocosts all show a trade-off between two important variables, labor and capital, good X and good Y. And also they depict what are called diminishing marginal returns. Diminishing marginal returns. So isoquants are represented by what we can call an isoquant map, which I illustrated to you earlier on. So what is the substitution effect with regards to isoquants? I said an isoquant shows the extent to which a firm in question has the ability to substitute the two different inputs that will, in order to produce the same output. So they depict two different combinations. So here you could have 7 combination 3. They're still giving you an output of 7. You could also have a combination of 2 combination 6, where these are labor units and these are capital units, or vice versa. So they depict that you are still able to, at some point, produce the same output, even at different points. So that's the main concept that we get from there. An isoquant map can also indicate a decreasing, increasing returns to scale, or they can also depict constant returns to scale. Now, what are returns to scale? We already said that the function of output Q is equal to labor and capital. So we have our alpha and beta. So if our alpha plus beta, when we add them, and the answer we're getting is 1, we call this the constant returns to scale. If our alpha plus our beta is greater than 1, we call this increasing returns to scale. If our alpha plus our beta is less than 1, we call that decreasing returns to scale. And what am I talking about? 15 marks, you are being asked to explain the concept of returns to scale using diagrams. So sometimes when you have an input combination of X or of labor and capital, economists have derived this concept as follows. Number 1, you can increase production from 10 to 20 to what? 30. We have 10Q, 20Q, and what? 30Q. what do you notice here? Production is increasing at a constant rate. So this is a constant returns to scale. We're increasing production at a very constant rate. So this means if we have our function could perhaps be L 0.1 K to the power 0.9. The total is giving us what? 1. So this is what we call constant returns to scale. Sometimes you could have production increase at an increasing rate. So here we have 10Q goes to 20Q. I said instead of going to 30Q, it keeps doubling. It has gone to 40Q. So this depicts what is called an increasing returns to scale. Production function could be epitomized by a function that could have, for instance, 0.3 and capital 0.8. So when we total up the powers, they are more than 1. They're giving us 1.1. As long as the total is more than 1, this is what we call an increasing returns to scale. So now we go to the other graph, which is going to depict another returns to scale. So we are going to look at the curves that are increasing. At this point, production will be increasing from 10. We have 10Q. Then when we go from 10Q, we go to 20Q. From 20Q, instead of going to 30 or 40, it has increased, but at a decreasing rate. It has gone to 25. So the differences are declining. So this is what we call a decreasing returns to scale. So you'll be writing a quiz anytime soon. So I need you to understand and appreciate this concept. So you could have your labor 0.3, the capital 0.4. You add the alpha and the beta, you're getting a total which is less than 1. So this is a depiction of decreasing returns to scale. Now, there's what we call an isocost, which is our budget line here. So a budget line follows a demand curve. So when you're given a cost, for instance, of 100 kwacha, and the labor costs 10 kwacha, so you put 10L, and the capital costs 50 kwacha, so you put 50K. So how do we draw this isocost? So this isocost, for all linear equations, whenever the letters are on one side, just divide them into the what? The constant. So you can put your capital here, your labor here, or vice versa. We're not strict. So the labor 10 into 100 is 10. So you put your point there, 10. 50 into 100 is what? 2. So you cut here at 2. So this actually shows a trade-off. If you're going to employ 2 units of what? Capital, meaning you're not going to employ any units of labor. So there's a trade-off that happens here. Okay? If you're foregoing 1 unit of capital, how many units of labor are you going to get for you to meet the budget? So here you have 1. under the capital. So how many units of labor are you going to get? We're going to substitute. Where there is K, we're going to put a 1. So 100 is equal to 10 L plus 50K. So where there's K, we're going to put 1. So we're going to solve for L. So 1 times 50 is 50. And the 50 goes aside, it will be 100 minus what? 100 minus the 50 that we have here. So when we subtract this, we're going to have what? 10L. So this side, we're going to subtract 100 minus 50 is 50. So here we're going to have 10L. So when we divide both sides by 10, what will our labor units be?
5.
5.
Our labor units will be at 5. So for us to employ one capital unit, we are trading off 1 for 5, because at this point A, we had completely 0 human capital or laborers. So now you decide to not to go to reduce your capital units from 2 to 1. You are increasing. You are doing a trade-off from 0 to 5 labor units. So this is what we call a trade-off. We're going to look at the example which is in the slides, so that we can try to illustrate this. So the company is producing widgets, and the cost of capital is 25. The cost of labor is 15. The total cost the firm is willing to pay is 150. Show the ISO cost. All right. So labor was how much? Capital was how much? And total cost was how much? Total cost was 150. Okay. And how much was the labor? The capital 25.
15.
Capital 25. And labor what? 15.
15.
So what becomes our ISO cost function? Somebody give us a function. What's the function we're going to use?
$150 is equal to 15L plus 25K.
150 15L plus 25.
5K.
So how are we going to draw this ISO cost? Tell me the intercepts for capital and labor.
Be 10, which is 150 divided by 15.
So on the labor, we're going to have what?
Push hard.
10.
10.
Then on the capital, we will have 6.
6.
6. Okay. Now question, how many units of labor are we going to have if we decide to downsize capital from 6 to 5?
Sorry, I'm a bit behind on how we're finding the 6 and 10.
All right, there's a question. How did you find the 6 and how do you find the 10?
Now, earlier example, you mentioned to say where we have letters on one side and the constant on one side, we just divide both numbers into the constant to get the plot, or get the actual figures that we.
Okay, so what she's trying to say is when this guy divides into the 150, it will give us the intercept for what? For labor. So 15 into 150 give us 10. So we have 10 labor units here. Then when this guy divides into 150, it gives us an intercept for what? For capital. So 25 into 150 gave us 6. Is that clear? So what do these intercepts mean?
Yes, it is.
If we're going to employ 6 units of labor, 6 units of capital, we're going to employ 0 units of labor, meaning we're exhausting our budget. If we're going to employ 10 units of labor, but we got 10, we're going to get 150, meaning there'll be 0 units of what? Of capital. Now my question is, suppose we're downsizing. What is the trade-off of foregoing 1 unit of capital from 6 to 5? How many units of labor are we going to employ? Quickly do your computations. Carol,
I got 8.33.
8.33. Okay. Please, if your husband is asking where you are, just tell them, honey, I'm in the BID class. They should not be BID. So 8.33, how did he get it? You simply put what? A 6 here. So 6 by 20.
5.
What did you get?
I'm saying I put a 5 there.
Oh, a 5, yeah. Put a 5 there. A 5 by 25. What did you get?
125.
125. So when the 125 went to subtract from there, what did you get?
What is 25?
5.
So 120. So 150 minus 125.
25.
So it's got what?
25.
15L.
Okay. So the difference here is 25. It's got 15L. So how do we get the L?
Divide 15 to 25.
What are we getting?
1.67.
6. 7.
So 1 point what? 67. So
67.
that's the correct answer here. We're going to get 1.67. Are we together? Are we all on board? Right. So include. So our isocost in this question becomes the curve at 6 and at 10. So the 150,000 is equal to 15L plus 25,000 K. So if we're going to calculate what we call our marginal rate of substitution, what is the marginal rate of substitution? Marginal rate of substitution, we divide the wage divided by the capital. So our wage over capital, it gives us 0.6. So it means for every 1 unit of labor the firm will hire, they have to give up 0.6 units of what? Of capital. That is called our marginal rate of substitution. So here there is 6 and here there is 10. Okay, so we're going to have K divided by the labor using the intercept. You divide 6 over what? 10. What are we getting? 0.6. This is called the marginal rate of substitution capital for labor. So it means for every 1 unit of labor, we are substituting 0.6 units of capital. That is how we can interpret that. Okay, so I will end here for my class today. I think this is where the slides end. We have been a good class.